The first type of special quadratics that we're going to talk about are called differences of squares. There's a pattern that you're always going to follow. It's always going to be two sets of parentheses, and one's going to have a plus sign and one's going to have a minus sign, but otherwise they're identical. The way that you get these other numbers is by taking the square root of each of term from the original problem. So the square root of x squared is x. That goes here and here. And then the square root of 9 is 3, and that goes here and here. So for this pattern, you have to have two terms. The actual word for that is a binomial. So if you have a binomial and it's a square minus a square, a perfect square minus a perfect square, and it's subtraction, then you have a difference of squares. One thing I want to mention is that if you have a sum of squares, so that would be a perfect square plus a perfect square. These are always prime, and prime means that you cannot factor it. So if it's a difference of squares with subtraction, it factors using this pattern that is up in blue. And then if it's a sum of squares, it's automatically prime. You don't have to do any work. So we're going to go through three examples here. Remember that all we have to do is set up our two sets of parentheses, one plus, one minus. It doesn't matter which one goes first. And then you take the square root of the original problem to figure out what goes where. So the square root of x squared is x, so that goes first in each set of parentheses. And the square root of 25 is 5, so that goes second in each set of parentheses. The next one is a square plus a square. So this one is automatically prime without us having to do anything because it is not a difference of squares, it's a sum of squares. For problem number 3, it looks a little bit different. It looks more complicated. It actually isn't all that much more complicated. So 1 plus 1 minus. The square root of 16x squared, we have to do two square roots. The square root of 16 is 4, and the square root of x squared is x. So I'm going to have 4x at the beginning of each set of parentheses. The square root of 49 is 7, so that goes at the end of each set of parentheses, and that's the final answer. This last one is a you-try problem, so I'll give that one a try and see how it goes. The next type of special quadratic is called a perfect square trinomial. It is a trinomial, as it says right here, so that means it has three terms. And the way that you'll know that it's a perfect square trinomial mostly is by looking at the first and the last term of the trinomial. If they are both perfect squares, it is most likely a perfect square trinomial. It's not a guarantee. There's something you're going to have to check. But most likely it is a perfect square trinomial. The way that you can factor this, there's a shortcut, is by taking the square root of the first term and the square root of the last term, and then you use the sign from the middle term. So the square root of x squared is x, so that's where these come from. The square root of 9 is 3, so that's where these come from. And then you take the sign from the middle, which is plus, so that's where these pluses came from. Now the reason it's called a perfect square trinomial is because it factors into something squared. So you'll notice that we have x plus 3 and x plus 3. It's the same thing twice. So you can actually just write it as x plus 3 squared since it's the same thing times itself. Now the thing I was talking about that you have to check. So I'm going to write this again down here. X squared plus 6x plus 9. We factored it into x plus 3 squared. The way that you can check is by multiplying the first and the last number. So if I take the first and the last number, so that's the square root of the first and the last number, but we already did that part, and I multiply them together, x times 3, usually we write it as 3x, and then if I take that number and I double it, so I'm going to multiply this by 2, I would get 6x. This 6x needs to match the original middle of your perfect square trinomial. If it does not match, it means that you don't actually have a perfect square trinomial and you have to factor it using a diamond. One nice thing about these perfect square trinomials is that if you don't recognize that it is a perfect square trinomial, it's not a big deal because you can still factor it using a diamond. I can still figure out what numbers multiply to 9 and add to 6. It would be 3 and 3. So anytime you do a diamond and you get the same exact number twice, it means you actually were factoring a perfect square trinomial, you just didn't realize it. But you should end up with the same answer either way. So this would be x plus 3, or you could write it as x plus 3 squared since it's the same factor twice. So we're going to factor these. The first thing we want to do is look at the first and the last terms. So for problem number 1, I have x squared and 16 as my first and last terms. Those are both perfect squares. So I'm thinking this is probably a perfect square trinomial. So if I take the square root of x squared, I would have x, and the square root of 16 is 4. Now if I multiply x and 4 together, I would have 4x, and then if I multiply that times 2, I would get 8x. So now you just have to check, does 8x match with the middle of your trinomial? And it does. So what that means is that this is a perfect square trinomial, so we can use the shortcut. And the shortcut is to take the two things that I used, my square root of the first and the last term. I use x and 4. I use the sign from the middle term, and then it's squared. So that's my final, my final answer. All right, now for the next one, I take the square root of x squared, which is x, the square root of 49, which is 7. Over off to the side, if I multiply those together, I would have 7x. If I multiplied that by 2, I would have 14x. So those do match. So I have 14x and 14x. Now it doesn't matter what the sign on 14x is as long as the number matches. So this one is good. So now what I'm going to do is take the two things that I originally got when I took the square root, and I'm going to put them in parentheses with the sign from the middle term, which is minus, and then I'm going to put a square on it. That'll be my final answer. Number 3 looks more complicated, but it's not. There's just one little tiny extra step we have to do. So again, I'm going to take the square root of 9x squared. It's a two-part thing. I have to take the square root of the number, which is 3, and then the square root of the x squared, which is x, and then the square root of 25 is 5. So I'm going to multiply those two things together. So 3x times 5 is 15x, and then if I double that, 15 times 2 is 30x. So here's 30x, here's 30x. That means they match. It's a perfect square trinomial. So now my final answer, I take the two things that I originally got, so 3x and 5. I take the sign from the middle, which is minus, and then I square it, and that's my final answer. This last one here is a you try problem, so give it a try and see how it goes. Just remember, you can always do these problems using diamonds. So if you don't recognize that it's a perfect square trinomial, it's not a big deal. It may or may not be a little bit more work if you don't see that pattern right off the bat, but you'll still get the same answer. Now we're going to talk about special cubics. We're going to talk about both the sum and difference of cubes. So when we were talking about quadratics, you can only do a difference of squares. A sum of squares is prime. When we're talking about cubics, you can do both the sum and the difference. They're both factorable. There are two patterns. And there's an example here of x cubed plus 125 and x cubed minus 125. I actually think this one's a little bit easier to see if you look at the pattern with variables. So I want to write that down at the bottom here. So instead of using x and a number, I'm going to just use a cubed plus b cubed. And what's going to happen here, let me write the pattern first, and then I'll show you what I'm talking about. So this would be a plus b, a squared minus ab plus b squared. All right, so the way that you get this pattern, you take the cube root of whatever your original problem is, okay? So in this example up here, the cube root of x cubed is x, and the cube root of 125 is 5. So this would be my a, and this would be my b. So then you just plug those numbers into this little formula here. Now the formula for sum and difference of cubes are the same. The only thing that changes are the signs. And down here where I'm putting a star, I'm going to show you a way you can remember that without having to memorize the exact formula both times. So the thing that you need to remember is SOAP. And what it stands for is same, opposite, always positive. And what that means is If you look at the original sign of your problem, the first sign that you need to use will be the same, the second sign will be opposite, and then the last sign will always be positive. So this pattern works again the same way if we're looking at a difference of cubes. So if I did a cubed minus b cubed, the only difference is that all these signs that I underlined in blue, except for the last one, because that one's always positive, are going to flip. So this is going to be a minus b. This is going to be a squared plus ab plus b squared. Now this middle term, when you figure out what your a and b are, that just means you're going to multiply them together. So let's go back up to this one at the top. I figured out that my a was x and my b was 5. So then I just plug it in. So this is going to be a plus b, so x plus 5. And then a squared, so I take my x, which is my a value, and square it. This is ab minus ab, so I just multiply them together. So 5 times x. And then my last number is always positive, and it's my b number squared, so 5 squared is 25. Okay, and it works the exact same way with difference of cubes, it's just that the signs are flip-flopped. All right, so we're going to do a few examples here. What I like to do is figure out my a and my b value, and then I'm just plugging it into the formula. And actually, before we start, I'm going to write the formulas up at the top. So if you have a sum of cubes, it would be a plus b, a squared minus ab plus b squared. And if you have a difference of cubes, a cubed minus b cubed, oh, I didn't need those parentheses, sorry. This would be a minus b, a squared plus ab plus b squared. All right, so back to problem number 1. The cube root of x cubed is x, and the cube root of 216 is 6. So now all I'm going to do is I'm going to use the red formula because it's a sum of cubes. And I'm just going to plug everything in. So instead of a plus b, I'll have x plus 6. If I square my a number, which is x, I would get x squared. Opposite sign from the problem. And I'm going to multiply 6 times x, so I get 6x. And then my last term is always positive, and it's going to be 6 squared, which is 36. So that's my final answer. I don't have to do anything else with it. One really nice thing about sum and difference of cubes is that this quadratic trinomial that you'll always end up with will always be prime. So what that means is we're never going to be able to do a diamond after we do something with that. It is possible that this binomial here, sometimes you might have to keep factoring it. So it might turn into a difference of squares or something else that you can keep factoring. So just be careful. So you might possibly have to keep factoring. Okay, so problem number 2. The cube root of x cubed is x, so that's my a value. The cube root of the cube root of 8 is my b value, which is 2. This one is a difference of cubes. So my signs are going to be the opposite, but as far as plugging numbers in, it's going to be the same. One thing you might want to try is to just plug in your signs right off the bat. So same, opposite, always positive. And now we can just plug in our numbers. So this is going to be a and b. This will be a squared. A times b would be 2x, and then b squared is 2 squared, so 4. And that's my final answer. All right, now this next one, a little more complicated, but not much. The cube root of 27x cubed is my a value. We have to do 2 cube roots. The cube root of 27 is 3. The cube root of x cubed is x. My b value is the cube root of 125, which is 5. This is a sum of cubes. So I'm going to do same, opposite, always positive. And now I'm just going to plug these things in. So I would have 3x plus 5. This term right here is something that a lot of students will make a mistake on. So be very careful. If I square 3x, I have to square both the number and the letter. So a lot of times people will write that this is 3x squared, but that is wrong. It should actually be 9x squared. All right, if I multiply 3x and 5 together, I would get 15x. And then 5 squared would be 25 for my last term. So that would be our final answer. Now the u-try is a difference of cubes. I'm not going to do the problem, but I will tell you that your a value is x and your b value is 4.